talk a little bit about our CCDEV 1 and 2 activities. Our CCDEV 1 agreement was a total of $3.7 million. In that period, we developed and demonstrated a composite pressure vessel. We did structural testing, both pressure testing and drop testing of that vehicle. And then we also did some development of our thrust vector control system for our escape system, which was later demonstrated under CCDEV 2. Under CCDEV 2, our Space Act agreement was for a total of $22 million. And there was 3 projects there. The Space Vehicle Design Maturation was to basically refine and develop the design for this biconic vehicle that will fly on top of multiple orbital launch vehicles. We did wind tunnel testing, we did aerodynamic analysis, we did propulsion definition, a lot of requirements for work with Ed and his team. Very, very good partnership on that refined that vehicle so we can take it further to the next steps. The pad escape test was the final milestone in our escape system development project, pusher escape risk reduction project, and I'll talk about that on a separate chart. And then our reusable booster system engine risk reduction test resulted in a full power level test, 100% power level test of an all-new American rocket engine that uses liquid hydrogen as a fuel. So let's go to the next chart, please. We'll talk about this engine, this rocket engine development. We call it the BE-3. It's a 100,000-pound thrust engine. It fits in between where the RL-10 and the J2XR. It uses liquid oxygen, liquid hydrogen as its fuels, and like I said, this is the first all-new American engine that uses liquid hydrogen as a fuel since the RS-68 development. It is deep throttling, it's restartable, and it's fully reusable. And under CCDEV 2, we did testing of the thrust chamber at NASA Stennis Space Center, E1 complex. The Stennis team has been a fantastic partner on this, and we always intended to continue working with Stennis after the CCDEV 2 agreement ended, our next entry into Stennis is going to be in the middle of February. We ran multiple tests over the full throttle range, going into the teens in terms of percent. And on up to full throttle, which is 100,000 pounds. And the result of this partnership was that we accelerated the development of that BE-3 engine by more than a year, because the facilities we've developed under private funding at our West Texas site are not set up to do these types of high-pressure testing. The facility at Stennis is a unique government asset. So getting back to what Phil was saying, access to these unique assets and these unique expertise is a significant benefit to companies like Blue Origin. While we were doing the testing on the TCA at Stennis, we were also testing the turbopumps, the liquid oxygen and liquid hydrogen turbopumps at our facility in West Texas. And now we have the engine fully put together, and the testing of that engine is underway at our facility in West Texas. This engine, I want to point out, is fully developed, designed and developed in-house at Blue Origin. We do the analysis, we do the design work, a lot of the fabrication, component testing, and then engine testing, of course. And I've talked a little bit about the development plan, but it's a pretty complex system, and there's quite a few other components to the engine development program. We're going to show a video of our test at Stennis. Before we roll the video, I just want to give you an idea of what you're going to see. You're going to see the engine, the thrust chamber fire from the side. When it ignites, it'll start out at the low throttle setting, and it'll step up in a variety of throttle settings up to full power. The total test duration is about 45 seconds, so if we can go roll the video, we can take a look at this. Again, we call this engine the BE-3. It's a liquid oxygen, liquid hydrogen engine thrust chamber, and full power setting is 100,000 pounds. So, and it's turbopump fed in its final configuration. But of course, in these tests, it's being run using the pressure of the ground facility. I got to hand it to the Stennis team again. They've done a terrific job, and I think if you had them in the room here, I think what we learned from them and what they learned from us is how to work in a commercial manner, how to speed up development, how to look at those assumptions that you've made when doing things one way, and then looking at when another company comes in and how you can accelerate your progress. We significantly ramped up our rate of testing over the period of this test program, and now it's getting multiple tests a day has been a significant benefit to us. So If we can go to the next chart, please. I'm going to talk about our crew capsule escape system risk reduction project. In October 19th of 2012, we conducted a full end-to-end demonstration of a pad escape system that will be used on our New Shepard suborbital vehicle, but it demonstrates the technologies and the integration required for an orbital system. The escape system is a pusher, and it pushes the crew capsule from the back to a safe distance away from the vehicle in the event that you have a mishap on the launch pad. We think this escape system is analogous to the airbag in your car. It's always there. It's lightweight, it's simple and reliable, and it's something that if you don't use it on a mission, you can just turn around and fly your vehicle again and again with a minimum of inspection. The demonstration here demonstrated, it showed the escape motor firing. It demonstrated our thrust vector control system, which was developed in-house at Blue Origin. The Aerojet provides a solid rocket motor. We developed the thrust vector control system and the aft closure for the motor. The guidance and control, the parachute deployment, the landing, and the recovery. Like I mentioned, this test was conducted with our NASA partners on site at our West Texas launch site on October 19th. And it was the only powered flight test under CCDEV-2, so we're very proud of that accomplishment. There's a few pictures at the bottom of the chart, but I want to pull up the video. And before we start the video, I want to just kind of explain what you're going to see. The vehicle is mounted on top of what we call the booster simulator. So it's sitting on top of a structure that represents the upper end of the booster that it's going to be escaping from. That booster simulator is fully instrumented. It's with load cells, pressure, and thermal sensors, so that post-flight we could reconstruct the environments that the booster vehicle will see in an escape, in an in-flight escape, or a pad escape. The vehicle itself, of course, was instrumented. This is a flight structure. You'll notice it doesn't have windows. It also doesn't have seats or life support systems, and that's part of our incremental development program. We wanted to have a flight structure in place, but we wanted to fly this vehicle in this pad escape environment, measure the loads in performance, and then use what we've learned from that to roll into our next version of the design. So let's go ahead and roll the video, and you'll see what we did. And this video is available on our website as well.
1, escape.
Now the vehicle pulls significant accelerations on the escape. It reaches about 2,300 feet altitude above ground. The parachutes deploy and it comes back. It landed within 7 feet of our predicted touchdown point. The winds were light that day, but we still are proud of the accuracy of the predictions we were able to make. Following some stabilization, the main parachutes disreef, and the vehicle descends slowly under the three main parachutes and touches down in the desert.
400. 300. 200.
It was a beautiful day, I might add. So.
100.
So I want to close up with the point. This has been a great commercial partnership. We brought money to the table, NASA brought money to the table, and we were able to do some things that are very useful, very effective, and help Blue to accelerate our progress. It's been a great relationship, and I'm happy to announce that we're working with NASA to extend our Space Act agreement in an unfunded manner, so that we can continue the relationship, continue to learn what we have from NASA, continue to allow them to learn from us, and that's something that we'll be working with them here in the coming weeks, and I'm very pleased about that. So, thank you.
All right, thank you, and thank you, Phil and Ed, and your entire team. It's an honor and certainly exciting to be part of this important new development effort. If we could go to my first slide. Our focus on identifying and mitigating risks early in CCDEV-2 really ensured we could mature the design to the point that we could accomplish a successful PDR and transition strongly into CC-ICAP. Our focus was across all of our subsystems to make sure we identified key design and risk drivers, and then perform the analysis and risk reduction demonstration testing that we needed to successfully mature that design. If we're looking at structures and mechanisms, we manufactured 2 iterations of our pressurized crew module, and we're able to do proof and leak tests on it, and also material testing to make sure that the design properties on the ASFORM material met all of our requirements. We conducted a number of composite material tests at higher temperatures just to make sure that the material would satisfy all requirements, and early micrometeoroid debris testing to help ensure that our thermal protection system design would satisfy all of our safety requirements. On the landing system, which is a combination of parachutes and landing airbags, we ran a number of 2 parachute drops and a large number of landing airbag drop tests just to make sure that design was safe and robust in all types of landing environments. Propulsion system, we ran a number of single-engine propulsion tests. The service module that we have is a disposable service module that handles not only the launch abort propulsion but also the on-orbit and entry propulsion, and ensuring that these legacy engines modified to our requirements would perform all the tasks early in the design cycle, really help buy down some development risks. And we also went out to Ames and the wind tunnel test and had a large number of runs and helped us build up our aerodynamic database to make sure the vehicle that we're designing could withstand the loads and was also controllable in all flight regimes. On to the next test. Another big focus on our effort to integrate with the launch vehicle. One of the things we did early onto the next page was to bring in the emergency detection system that's being designed and built by United Launch Alliance for incorporation into the Atlas V launch vehicle, and run early testing on an EDS emulator integrated with our software and our flight computer to make sure very early in the software development process that the 2 systems were compatible or could talk to each other and would satisfy all requirements. We also ran a number of integrated tests between our flight software system and our autonomous rendezvous and docking system, which obviously is a critical piece of this development effort to make sure that those systems were compatible and would meet all requirements. And a large effort on identifying different options for our cockpit, and then moving quickly at the end of CCDEV2 to finalize that cockpit design with a number of human factors tests in the cockpit to make sure that all of the panels were laid out correctly. We could satisfy not only normal mission operations but also anomalies that the crew could expect to encounter. So a lot of work, just making sure we identified those risks and were comfortable moving into CCI-CAP. Going to the next chart. The real focus of CCI-CAP is final design maturation and moving into a quality critical design review. And so our focus was laying out a plan that integrated key milestones across all of the different development segments, both spacecraft, the launch vehicle, obviously, which is critical to us, but also production and operations. So across this entire plan, we've got a number of very important and milestones that we have that our team is working on to accomplish. In January of this year, we've got 2 milestones actually. In the next couple of weeks, we'll be releasing our first flight software iteration of our on-orbit configuration, and the team is in the lab now running tests on that, and it looks like that is moving along real well. And then later on this month, we'll also be conducting, actually next week, our landing and recovery and ground communication design review, just to make sure we have the plans and the equipment and the infrastructure we're going to need, not only to communicate from the ground, but also to safely recover and transport the capsule after it's landed. Looking at some of the others, we'll move very quickly into a preliminary design review with United Launch Alliance. one of our key partners on the launch vehicle adapter. That'll be the adapter plate between their launch vehicle and our capsule. We'll be going back and doing more wind tunnel tests. In fact, we've got 5 different wind tunnel test series between March and August of this year, just so that we make sure we have a healthy and robust aerodynamic database so that we can finalize